Right, welcome back. This is 8.1.5b. In this chapter, we are talking about linear transformation and eigenvectors with respect to eigenbasis and change of basis. You will need to refer to 8.1.5a first to revise, as well as 8.1.5b work example. For a recap, in the first few chapters of our course, what we did was given a system of linear equations, we form A from the equations and Y from the given values, and we are asked to solve for X, the unknowns. However, in linear transformation, although we are still observing the same equation, it is of a different nature. In this case, the input to the system is X. A is the model or the linear transformation we're trying to design, and Y is the targeted output. So the focus is now on what happened to X when A acts on the X to get Y. When we say that the system when the system is linear, what we are trying to mean is that we have x1 plus x2. It can be decomposed into x2 or a alpha x1 plus beta x2. Then it can be composed into alpha a x1 plus beta a x2. When this behavior occurs, we say that the system is linear. So in this course, we are only talking about linear transformation, and A here, representing the linear transformation, is simply a matrix. Abstractly, when X belong to a vector space V and Y belong to another vector space, for example W, then transformation of X is from V to W, for example. If the system is linear, then A can be a matrix representing the transformation T. The input X can be represented in the standard coordinate, where, for example, if there are n number of independent components to represent the basis of V, then X can be represented as a vector in Rn space. So whether X is abstractly in the vector space belonging to V, or X belonging to Rn, where Rn is the vector space representing V, it is the same. So abstractly on the top, X is being acted on through T, so we write Tx, and Y is this. Similarly, we can use a matrix A to represent T, and Y can be written as A times X to represent the linear transformation. Now in this case, if the input is Rn and the output is Rm, therefore A must be a M by N matrix. If you're wondering about the columns of A, what is A made of? A is a matrix of M by N dimension, and each of these columns of A is the linear transformation T acting on the identity matrix E1, E2, where E1, E2 are the columns from the identity matrix. E1, E2 up to En are the standard basis for Rn. Right, so in this slide, we understand that the linear transformation T can be represented concretely by a matrix A of dimension M by N, given that X belong to Rn and Y belong to Rm. Right, we'll leave you to read the proof here, why the Tx can be represented as a matrix product A times X. Briefly, if X can be represented as Rn, an element of Rn, then we write it as a column vector where each of these elements x1 to xn are the real numbers. Now we want to find out why tx can be represented as ax. The first idea is we decompose the vector x into its bases. This is e1, this is e2, and this is en. This is the standard basis because each of these bases or each of these column vector only have an element 1 and with the rest 0. The second one is 1 in the second coordinate, and the last one en is the 1 in the last coordinate. Since x can be decomposed into linear combinations of the standard basis, then the element x1, x2 are simply the elements of this vector. Now, because t is linear, whether t acts on the original x or operates onto the linear combination, it does not matter, because remember, when a system is linear, then this operator can move inside and operate directly on the basis. Because now we treat xi as a scalar and we can bring it out. Remember, what we are trying to do here is alpha x, where alpha is the scalar, so it can be t of x. And then the other property that we are dealing with is alpha x plus beta, let's say x1 and beta x2, and now we are doing alpha t x1 plus beta t x2. So we use the property where t is linear so that we can achieve this effect. T of x is simply the scalar of each coordinate multiplied by t on each basis, and we sum it up. Now, we can therefore now define the matrix A in this form, where each of the columns of A are these. And once we have this, then when we multiply A with x, so this is the matrix A with a column vector x, then you will see that it is exactly this form, therefore leading us to understand that A times x, with A defined this way, is same as t of x. This is the proof. Thank you.